Welcome back to a new video. In this video we will discuss the one-port networks in electric circuits. We will discuss how we can determine the resistance looking between two nodes for a complicated electric circuit. And for that we will use the matrix notation, and we will see that shortly in our calculations. Of course, we will work out some calculations and examples step by step, and also verify these in SPICE simulations. So let's look at our first example. Example number 1, we would like to calculate the resistance between the nodes P and Q for this circuit. This is a rather simple circuit. I actually don't need the matrix method I will demonstrate right now, but it will illustrate the second example in more detail and also the motivation for using that matrix method. So we will see we have now in this case 5 resistors, R1, R2 up to R5, and we will like to determine, as said, the resistance between P and Q, which is an RPQ. So how we can determine this? Let's look at our solutions. For that we will use, in this case, the first step is the mesh equations. So we will set up the mesh equations or mesh current equations. Now for that we need to make loops. That this is the first loop, IA loop, and we have another loop for this, IB, and there is another one, IC. So we have 3 loops. Now we will now set up the equations here. The first one, loop A, that will be then R1 times this current IA, but then IB is then actually fighting that direction of IA back, so it will be then minus R1 times IB, that is 0. We have the value for the R1, so we can just substitute this, and we have now our first equation. And remember here, don't reduce that to IA minus IB is equal to 0, because we need to keep it as it is and then set up the matrix equation later. For loop B we do similar. So what we see is actually that now the IB is our reference direction. Now the IA is fighting back. That means we have now here R1 times the minus of the IA. That's the first equation. But IB goes through R1, R2 and R3, so those are all positive in the parentheses, times IB. And we also see that IC here is also fighting the back, so it's in the opposite direction of IB. That's why we have here minus R3 times IC. Again, everything added to 0. Now let's also substitute the values in here. For R1, R2 and R3 we have this, and that will be then reduced to this equation. Again, we don't simplify this at all, and then we keep it as equation number 2. Now the final loop is loop C. We see that the IC is going again in clockwise direction, but that is our reference direction. But now the IB is fighting back, because this will go up and this will go down. So we will have minus R3 times the IB, and then R3 plus R4 plus R5 in the parentheses, everything is plus, times IC, that will add up to 0. Again, substitute the values given, we will have this, and that will add up to minus 5 times IB plus 30 times IC is equal to 0. Again, don't simplify this by dividing by 5 or minus 5 to the left and right hand side. Just keep it as this, and then name it as number 3 equation. Now we will now set up the matrix format, step 2, from these 3 equations. This is now matrix we have set up. We just call it just A. You can also call it another letter. We see the first equation, 20 and a minus 20 and also 0, because there is no IC. That's the first row. The second row is minus 20, 31 and a minus 5. That's what it is. And then we have here 0, because there is no IA here. It will be a minus 5 and a 30. That's shown here. Now we will now create as a second matrix, which will be then, this is a 3 by 3 matrix, will be a square matrix. The other one will be 2 by 2 matrix, which will be then created from this matrix by eliminating the first column and the first row. That will be then 31 minus 5, 30. And that is what we call here A11. That's this. Now the next step is determine the determinant of this matrix and also the determinant of this matrix. Now determinant of this matrix, A, is determined like 20 times the determinant of this part, which is shown here. And then minus 20, because you will actually change the sign for each step you make. So that's then a minus 20, and then you lose these parts. So you only have these 4 values here. And the third one is 0, so I just added them here for completeness. And now we need to determine the determinant for this part, which is then 31 times 30 minus 5 times minus 5, and the similar operation here. That's all shown here in detail, and that will add up to 6,100, and then the units are ohms to the power 3, so ohms cubed. Why? Because we have actually here a 3 by 3 system, which will then result in a unit of ohm cubed. In a similar form, we do the determinant of A11, but which is actually this part, which is already done here, so that can be done faster, which is then this given here, and that will give us 905 ohms squared. Now we would like to calculate the resistance, which has a unit ohms. That means we need to do here determinant of A divided by the determinant of A11. So then we can calculate the RPQ using this formula. Now we have now these two, so the blue one and the red one. We can set up in the equation. We have here now 6.74 or 6.74 ohms. Then looking between the P and Q. Now you can check this by doing this in the classical way by adding the R4 and R5 and then taking that to parallel to R3. Again, add that in series with R2 and take that again parallel to R1. You will get the same result, which is maybe also faster than this method, but this is again to illustrate the concept for later, more complicated example. But let's now verify these in the simulation results, because we had this 6.74 ohms. This is another simulator. You see the values, 10 ohms, 15, 5, 6 ohms, and 20 for the resistors. You see in this case that the ohm meter is indeed measuring 6.74 ohms, so that is now checked. This is our first example. Let's now move on to the second example, which is more complicated. The only addition compared to the first example is this resistor 6 here, which is here now in parallel between this node and that node. And that is now 11. So the rest of the values are exact same, only the resistor 6 is added here. Again, the same problem. We like to determine the resistance between the nodes P and Q. Again, we will use the matrix method and we will look at the solutions. First step is, in this case, we will use a method, which is called in this case just method 1, where we use the loops. So we again use the mesh current method, but I will also for the same circuit, which is then in method 2, where I use the node voltage method, which is then faster in this case. So let's go through the equations first. Again, the loops IA, IB, IC. In this case, we have also a fourth loop because we have also the resistor 6 here, which will give us now 4 equations and 4 unknowns. Okay, adding and then setting up the equation for loop A in a similar form, exact same as before. So again, plus R1 times IA minus R1 times IB is equal to 0. Again, substitute the values, you get now this, and this is our first equation. Loop B, here, looking here, then we have IA is fighting back, but IB is now our reference direction, but also IC is fighting back, and also ID is fighting back for R2. So you can see the resistors and also the associated currents that are fighting back. Okay, that is for the equation here. Let's substitute the values here given, and that will then produce this equation, and we call this equation number 2. Loop C, in a similar form. For this one, you see the current C is now our orientation, reference. IB is fighting back for resistor R3. Our ID is fighting back for resistor R4. That's all shown here. So minus, there's no IA here in this equation. So let's again substitute the values here. You see this, and that will add up to this equation. And we call this equation number 3. The final one is this loop. In this case, the ID is now our reference current direction. But now for R2, resistor R2, the current IB is fighting back. And for resistor R4, that's IC is fighting back. So we will see again a minus signs for the R2 and R4 here. And the addition of R2, R4 and R6 here, that is positive for ID. There is no IA, again, contribution here. Now let's also substitute the values here. and that will give us this expression, which is then our fourth equation. Now, the step 2 is setting up the matrix format. We will see that we need a 4 by 4 matrix because we have 4 equations and 4 unknowns. That is then more complicated, of course, but we will see that's 20, minus 20, and 0 because there is no IC and ID for the first equation. That's shown here. In a similar form for the second equation, you see all the coefficients. Third one, there is no IA here, and also for the fourth equation. Okay, now we have everything. In a similar form we did for example number 1, we will now also determine the matrix A11, which will be created from this matrix by eliminating the first column and the first row. That's shown here, so you will only have the 31, minus 5, minus 6, minus 5, 30, minus 15, minus 6, minus 15, and 32. Now we will determine now the determinant of this matrix A and determinant of this matrix A11. And then the ratio of these two, determinant of A divided by the determinant of A11, will give you the required resistance between the P and Q. Now determinant is then shown here. So we go, let's say, by this row. You can also go by this column. It doesn't matter how you go, but this is more efficient because we have here 2 zeros. That's actually shown here. So and then you create from this matrix first this part, which will be then again a determinant part. And then for this minus 20, because you change the sign going from this to that, and that will give you then this expression. And then the third and the fourth one are all 0, so that's given here for completeness. And then working out this is really straightforward determinant business for linear algebra. I will just also show you the results here in great detail, and then we will add up to this value, which is in this case also a 4 by 4 matrix that will give us a unit of ohms to the power of 4. And the values here is 106,100. Now the other matrix, which is then the determinant of A11, which is in similar form, actually what we did here, and that will give us here 20,005, and then the units are ohm to the power of 3. Then we can now calculate in a similar form as example number 1, the resistance between P and Q, which is the determinant of A divided by the determinant of A11, which is then this, and it will give us 5.304 ohms. Okay, let's now check that this is indeed correct in the simulations. This is what we just calculated, and this is the simulated result. You see the R6 here in the circuit added, which is 11 ohms. And now you'll see that the ohm meter between these two nodes, which are the P and the Q, indeed measuring 5.304 ohms. So that is also checked. Now we will do the exact same circuit using another method. So in the solutions we will see that we have now a second method, which will use the node voltage method. So we will set up the node equations for our first step. For that we need to designate some nodes. I will designate this node A, another one here, node B, and also node C. So we have discussed this also in the node voltage analysis examples. Now we will now set up the equation. For that we need to also set up the polarities. So this current goes like this. This is just a choice. Another one is going like this. This current is going like that for R3. R4 is going like that. R5 is going like that. This is just really a random choice. You can choose also the other directions. It doesn't matter, it will work. So I have now 6 current directions. So I will set up now the current equation for each node here. So I will get 3 equations instead of 4. That's already actually saying that this will be an easier calculation compared to the first method. So first, the Kirchhoff's current law, or the the current node equation at node A. Now what we see is I1 is leaving, I2 is leaving, and I6s are leaving, so we can just add them up in this case and then equate that to 0. That is really the Kirchhoff's current law. And I1, I2, and I6 can be then rewritten in the volts over resistance, which is then using Ohm's law. Similar format, so VA over R1. And then this voltage is of course VA minus VB over R2, and this voltage here is VA minus VC over R6. That's all shown here. We can now group the coefficients for VA, VB and VC together, that's shown here. And then substitute the values we have given, that's here, and then make it more exact. That will give us these values. These are the exact values, and that is now what we use later in our matrix format, and let's call this equation number 1. In a similar form, we go for Kirchhoff's current law at node B. Now I2 is moving in, so I call this just positive, but what's leaving I call this negative. Of course I did this here also positive, positive, positive for leaving, but I can also do negative, negative, negative is equal to 0, but then you can multiply left and right hand side by the minus sign, so you will get exactly the same result. So it is easier to work with plus, let's say positive signs than negative signs. That's the reason for doing that here. So that means I2 is moving in and I3 and I4 is moving out, so that's minus and minus for I3 and I4, again adding up to 0. Again the same procedure, so you will now change the current equation in volts over resistance for each one. That's shown here, so VA minus VB over R2, and this is VB over R3 only, and then VB minus VC over R4. Again a minus sign, so don't forget that. So we have this, again group the coefficients for VA, VB and VC together. That's shown here, and now substitute values here, and then again make it more exact, actually in exact format. That will give you this one. This is now our equation number 2. The final one for this node C, what you see is that I6 and I4 are coming in this node, but I5 is leaving. That means I4 minus I5 because that's leaving, and then plus I6. And then again adding up to 0. Again we will set up the equations using volts over resistance, so actually each part is using Ohm's law, and then group the parts for VA, VB and VC again, so this is really straightforward, and then adding the values from the given here, and then again make it exact expression, and then you will get this. And that will be then our third equation. Now we will see here that we can again set up the matrix equation for these 3 equations. So this is now the matrix equation, which has in this case some fractions, a lot of fractions actually compared to the first method, but it is now 3 by 3 instead of 4 by 4. So again you see the coefficient here, 203 over 660, etc. And that's all for the other one, 1 over 6, etc. also for the other one. And this is 1 over 11, 1 over 15, and minus 17 over 66. Now, this is now our the matrix A, but matrix A11 will be created from this matrix by eliminating the first column and the first row. That means we only have these two. We will get now also 2 by 2 matrix. But first, let's determine the determinant from this, again in a similar format. And then again you do this cross multiplication minus the cross multiplication here, and then times this coefficient in front of it, the similar form here and there, and that will give you 20.207 millisiemens cubed, because this is a conduction, so the units are 1 over ohms, or in this case in S. Now in the similar form for the other matrix I just described for creating the A11, again the determinant, which is then this cross multiplication minus the multiplication of these two, which is shown here, and that will give us 10.717 millisiemens squared. So we get now here a conduction cubed and a conduction squared. Now in order to get the resistance, which is then in ohms, we need to do determinant of A11 divided by the determinant of A. Because if you do the determinant of A divided by the determinant of A11, you will get still the unit as conductance. We then need to invert that. So we'll do that right away. That means there will be then this. So, and that will give us the following result, which was also what we had determined in the example number 3. I mean in the 2 of course, but in this case it's example number 3, but for the first method, and you'll see that this is indeed correct. And this was our simulation result, so let's get back to the simulation result here. Now for this node multi method, again getting back and producing this, you see that in this indeed correct. Alright guys, this is our example set of 3 examples where we consider the determination of the resistance between 2 nodes by matrix method, which is called in this case one-port systems. If you have any questions, comments about these examples, please let me know. I will try to answer them as soon as possible. See you next time in another video. Take care.